We're going to learn about normal force and apparent weight. Here we go. This whiteboard, although it looks reasonably solid, it consists of nothing but atoms, and these atoms have big spaces in between them. In fact, this whiteboard is mostly space. Yeah, you got atom, 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 but mostly space in between. My hand, here I'll get in front of the camera. My hand is mostly space, correct? Sure, it has atoms, but it's mostly space. So here's what I'm going to do, something you've probably never seen a teacher do before. I'm going to take my hand, which is mostly space, and pass it through that whiteboard, which is mostly space. Are you ready?
Yeah.
Here it comes. It's going to take a little bit of concentration. Okay, great. Here we go. Okay, well, maybe I wasn't concentrating enough. I'm going to close my eyes while I do it. Okay, it's not happening. Tell me, why not? Mostly space, mostly space. Why can't I put my hand through that wall? True. Normal force is the correct answer, but I want you to tell me specifically what's happening, like what's happening on an atomic level. Consider the structure of an atom. I want to remind you, or you remind me, what's the structure of an atom? What does an atom consist of?
Protons, neutrons, electrons.
Good. Protons, neutrons, electrons. Where do the protons and neutrons live?
In the center.
Yes, and where do the electrons live?
On the outside.
Yeah. So tell me, why is my hand not passing through that wall? What force is preventing my hand from passing through the wall? What's that? Tell me more. What kind? Thank you very much. Electron repulsion, right? It's electrostatic repulsion. You guys get that? All of my atoms have these big electron clouds, and all of these atoms have these big electron clouds, and these electron clouds get repelled by those electron clouds. And I can't get my hand in there because of all these electron clouds repelling all of my electron clouds, right? Well, there's a name for that force. We call that normal force. When two things are pressed together, they do not pass through each other because of this electrostatic repulsion, because these electron clouds repel these, and so whenever you press two things together, they exert a force on each other, and that's normal force. Now, why do we call it normal force? Well, those of you who have had higher math, do you know what the word normal is a synonym for? Yeah, perpendicular. So it's called normal force because the direction of the force is always perpendicular to the surfaces in contact. These surfaces are vertical surfaces, so the normal force they exert on each other is horizontal. The normal force is always perpendicular to the surfaces in contact. So hey, let's go ahead and define normal force. Normal force. It's the force that two objects exert on each other when they are pressed together. Force two objects exert on each other when they are pressed together. Good. And the direction of that force is perpendicular, that is normal, to the surfaces in contact. Direction of force is perpendicular, that is normal to the surfaces in contact. Great. Let me get a picture of water. The symbol that we use in this textbook for normal force is F sub n with a capital N. That's the symbol I'm going to use for normal force. In the same way that for weight, I ordinarily use mg for weight, because weight is equal to mass times gravity. I'm going to use F sub n for normal force. please do not call this natural force. Although normal force is only natural, we don't call it natural force, it's normal force. If we call it natural force, you'll be very embarrassed. Okay, hey, let's do a problem. Here we go. I have a 5 kilogram mass. And this 5 kilogram mass is sitting on some surface, a table or the floor or whatever. Let's do a free body diagram. What forces are acting on this 5 kilogram mass? I don't know. Someone left an umbrella in here. Do you think a friend might have taken your bag?
I probably left it in my purse.
Oh, wow. Oh, it's like a little bag, not as like backpacks. Okay, free body diagram. How many forces are acting on this weight? Two, right? Gravity and normal force, correct? So let's go ahead and make a drawing. I got normal force acting up. Here's my big fat dot. And I've got the weight of this object acting down. Great. What's the acceleration of this object? How do you know its acceleration is 0? Yes, it's at rest. If something's either at rest or moving in a straight line constant motion, then the acceleration is 0. Alrighty, I'm going to define up as positive, and then I'm going to do sum of the forces equals ma, and I'm going to find what the normal force on this box is. I'm going to list my forces, normal force minus mg. The normal force gets to be positive because he's pointing upward. Mg has to be negative because he's pointing downward. Then I got the mass times the acceleration, but the acceleration is 0 because it's at rest. And so my normal force ends up equaling 5 kilograms times 9.8 meters per second squared. That is my normal force is 49 newtons. Please notice, the normal force ends up equaling the weight of the object. Is this always going to be true? Is normal force always going to be the weight of the object? I mean, like, look at me. I weigh 260 pounds. I'm not accelerating anywhere, so how much normal force must the floor be exerting up on me? 260, right? So again, my normal force is equal to my weight. But is that always going to be true? Why not? Noelle, you shake your head. Can you give me a scenario where it wouldn't be true?
Well, anytime when you have an acceleration that isn't 0.
Oh, you're so smart. Oh my God. She's right. If the acceleration is not 0, then the normal force isn't going to be the same as the weight. For example, here, let me get a 1 kilogram mass. Right now, tell me, this is a 1 kilogram mass. This is a 9.8 Newton mass. Okay, 9.8 Newton weight. Right now, what's the normal force of my hand on this weight? 9.8. But what if I throw it up in the air? What if I accelerate it? While this thing is in my hand accelerating, what must be true about the normal force of my hand on this weight? Yeah, it's got to be greater than 9.8. That's the only way I can accelerate it upward, correct? So yeah, you're right. Let me give you another scenario where normal force isn't equal to the weight of the object. Here, same 5 kilogram mass. Only now I'm going to have a rope attached to it. And that rope is pulling up with 20 newtons of force. This mass is still sitting on a table or floor, whatever it is. But I've got a 20 Newton force up. So how many forces are acting on this mass now? 3. Good, 3. There's 3 forces acting on the mass. I'm going to ask you to find the normal force, but first I need to show you what the free body diagram looks like, because you've never had this sort of thing before, not often. Here comes the free body diagram. Here's my 5 kilogram mass, that big black dot, big fat dot. And there's 2 forces upward. There's that 20 Newton force, and there's normal force. And I don't even know which one's bigger or which one's smaller yet. But when you have two or more forces acting in the same direction, try to make them parallel to each other, which may mean you having to make your big fat dot bigger and fatter, and that's okay. But you need to show all forces as being distinct separate forces. You got the 20 newtons and you got the normal force. And then finally I've got mg. You guys okay with that free body diagram? And this way is positive. I'd like everyone to please do sum of the forces equals ma. Go ahead and find me what the normal force is now. I'm going to walk around and quote unquote help you. We're so smart. Wait a second. Okay, but what is A? Oh, it's 0, okay. Got some crazy math going on though. Because if that's minus mg, if you're going to put it on the other side of the equation. But what have you done? I don't know. Easy, you're on your own. I don't know what's wrong.
Yeah. So,
Yeah, 29 squared.
Wait, is this already?
No, it's not accelerating, it's the rest. Yeah, the guy's sitting on a table.
Okay, so if you find that.
Good for you. It'll never change. Good for you.
That's how I said it.
Okay, yeah, everything you have here is correct. Now just solve for normal force. Yeah, beautiful. Okay, good. I mean, you don't need those parentheses around the F sub n and 20. Okay. Yeah, everything you did is perfect. I got no argument with any of it. Yeah, no, you're good, right, except, yeah, that's all correct. Now just do the consequences. Okay, do multicolor. Okay, this is correct. Now just plug in the 5 for the M, 9.8 for the G, and solve for F sub n, and you get the You're so smart. On the left side, you've got 20 meters and F sub n, but you also got minus mg, so don't forget that. Oh wait, yeah, let me have the other side. Yeah, put minus
So you're gonna
mg.
add the energy to this other side and subtract the other. I mean,
I did it over
You guys-
here.
you guys-
I did it.
Right, good job.
I don't remember that.
You guys have-
Question about it.
you guys- you guys have all your forces.
F sub n
Oh, yeah,
plus 20
yeah.
minus mg. That's right.
You have to say that. I think you explain the whole.
Can you finish that writing?
I'm on my forces. I don't want to read them stuff.
I literally just forgot to put a plus.
This line here is totally correct. And so, and the acceleration is 0, so it's going to be, when you put it on the side of the
Can we still order those?
We need a list of people.
We just need Travis to divide it. But they, in your English class, they would.
I'm hoping Sandy and our Mason can make it.
But you know, because I need to call back. You know, but I don't know.
Here's the thing, right at the very start, you should include all the forces on the left side. So it should be F sub n plus 20 minus mg, all to the
Hey,
left.
Mason.
Yeah, there should be 3 things on the left side of that equation. Okay, beautiful.
Never mind.
Oh, Mason.
I'm embarrassed now.
Your class leader.
Yeah, that's good.
No, the question is that you are one. I'll tell you more after.
You and Zach. You guys do it. Yeah, but that.
Okay.
That's like, yeah. What you got?
Okay, guys, as you see, even if something's at rest, oh, is the camera still going?
Yeah.
Good, good. Even if something's at rest, your normal force isn't necessarily your weight. In fact, almost never will the normal force be actually the weight. One thing that the students in this class are really good at is realizing that on the left side of the equal sign go all the forces. Even though this says mg and that has ma, and you go, well, maybe this guy should be on the right side of the equal sign. Don't do that. Make sure that all three of these guys are on the left side of the equal sign. Up is positive, so I got F sub n plus 20 newtons minus mg, and then we got m times 0 because it's not accelerating. So I got normal force equals minus 20 plus 5 times 9.8, and I got my normal force being 29 newtons. And like I said, virtually everybody got that just fine. Alrighty, so hey, that's normal force, and we'll be experiencing normal force a lot. Let me give you a scenario. Let's say I am bench pressing. So I'm here. Just a second. Okay. Okay. I'm bench pressing, and then somehow the weight slips and it falls on my chest.
Oh, boy.
So now I've got 200 pounds resting on my chest. Now, what kind of force is the barbell exerting on my chest? What classification? Yeah, normal force, right? So it's exerting 200 pounds of normal force on my chest. So I'm going, help, okay? And then someone comes by and says, I'll help you. And I say, please lift this 200-pound weight off of me. And this guy says, well, sorry, dude, but I'm only able to lift 199 pounds. So I can't help you. What am I going to tell him? What's that? What's that, Alexis? No, go ahead.
I was going to say, can you not push up the other?
Well,
No,
yeah. I mean, what if he exerts a force up of 199 pounds? Then the normal force on my chest wouldn't be 200 anymore. Cheyenne, what would it be?
It would be 1 pound.
Yeah, 1 pound, and that's good. That's better than 200. So I would tell him, dude, please exert your 199 pounds. I'm okay that you're not lifting it off me completely. Just lift it off me some. You see what I mean? Because you want to reduce the normal force that your chest has to exert up on the barbell to hold the barbell up. Without the guy, my chest is exerting 200 pounds up to hold up the barbell, which means the barbell's exerting 200 pounds down on me. That's not good. Okay, you guys get that?
Yes.
Alrighty, then let me see what comes next for you guys. Okay, rocket propulsion. Okay. Rocket propulsion. In order for something to accelerate upward, something has to be exerting a force on it. There has to be a force on something in order for it to be going upward. So here's my rocket ship. Okay? And you know a rocket ship has fuel coming out the back. Tell me, what is the rocket ship pushing on in order for it to accelerate upward? What's that, Jonathan? Jonathan says the ground is pushing against the ground, like the same way that if I jump in the air, I'm pushing against the ground. How many people say that's how rocket propulsion works? It's pushing against the ground. Not many of you, huh? Okay, well, people in the 1600s, they actually believed that. They believed that a rocket has to push against the ground in order to go up, which means your rocket ship can't get too far from Earth, or it loses, the ability to push against the ground because it's so far above the ground. So when people said, I'm going to fire a rocket to the moon, they would scoff at them because they'd say, hey, you know, you're going to be too far away from the ground. You can't push against the ground anymore. The rocket ship will not get you to the moon. Well, if it's not the ground, what is the rocket ship pushing against? The atmosphere? Who said that? Imani? How many people say it's pushing against the atmosphere? Cool. Like the way a bird flies, right? A bird's wings push against the air, or an airplane propeller or helicopter push against the air. But here's the problem. Once you leave the Earth's atmosphere, how do you get all the way to the moon if you can't push against the air anymore because there is no air? Right? I mean, your rocket ship, it can't push against the air anymore once it leaves the atmosphere. So that can't be it either. To answer this question, I'm going to tell you about my rocket ship, the Mr. Shana designed rocket ship. Here's the rocket ship I have designed. Okay? It consists of the rocket ship, a chair, Mr. Shana sitting in the chair, and then a room full of bowling balls. Okay, and here's how my rocket ship works. And let me bring over this chair. Here's the chair I'm sitting in for my bowling ball rocket ship. And what I do is I pick up a bowling ball and throw it out the back as fast as I can. Then pick up another one and try to do it with as high a frequency as I can. And I'm constantly pushing bowling balls out the back. Now tell me, I don't have a bowling ball here. The only things heavy enough to propel me are things that when they hit the floor, they'd make a really big sound, so I can't do that this year. There have been previous years that my spinning thing, that big metal thing you stand on and spin, I've used that. I throw that, but I can't do that here or I'll destroy the floor and disturb the teacher downstairs. But if I were to pick up something soft, maybe my daughter, my 8-year-old daughter, and I threw her that way, what would I do? I'd go that way, right? If I threw my daughter this way, I would go in the opposite direction. Why? What force is propelling me in the opposite direction? Thank you. Her force specifically. What classification? What kind of force is she exerting on me? Thank you, Imani. Yeah, normal force. You guys okay with that? I'd push her that way, and by me pushing, exerting a normal force on her in that direction, she would exert the same force back on me. And that's what I do with my bowling ball rocket ship. I just keep pushing the bowling balls out. I exert a force on the bowling ball exerts a force back on me, and I get to go in the air, and I go all the way to the moon. As long as I got enough bowling balls, and I keep throwing them out with a high enough frequency, I can get all the way to the moon with my bowling ball rocket ship. Does that make sense to you guys? So let me ask you the question again. These rocket ships, they're not pushing against the ground, they're not pushing against the atmosphere. What are these rocket ships pushing against? Yeah, itself. Specifically, the fuel, right? These rocket ships are pushing against the fuel. And so if anyone is asking what propels a rocket ship, tell them normal force. Because the rocket ship pushes the fuel out the back. The fuel goes really, really fast, not like bowling balls, it's extremely fast. The rocket ship pushes the fuel out the back, and the fuel pushes back on the rocket ship, and the rocket ship goes in the air. And that's how rocket ships work. No different than my bowling ball rocket ship, only way better. Let me give you another way to think of it. If I took rocket fuel in like midair and ignited it, it would explode in all directions, right? But this rocket fuel doesn't explode in all directions. It only explodes downward because the rocket fuel is contained by the rocket ship itself. Why does it only go downward? Because the rocket ship is making it go downward. The rocket ship is pushing it downward just by its physical design. And so because the rocket ship pushes it downward, the rocket fuel pushes back upward, and that's why we get to have rockets that go all the way to the moon. Because you're pushing against the fuel, you're not pushing against the air of the ground. Does that make sense to you guys? Hope so, because that's it. I waited to tell you about rocket propulsion until we learned about normal force. I was then going to give you a rocket problem, but you know it's the same as this other stuff, so I'm not going to do that. I'm going to go on to another topic, which is apparent weight. Okay. Alrighty. Apparent weight. I'm in an elevator, or you're in an elevator. Under what circumstances would you feel heavier than you normally are? What's that, Gavin?
When it goes up.
Not just when it goes up, but tell me more. It's when specifically.
When it stops.
What's that?
When it stops.
Okay, let's think about that. We'll talk about that. In your mind, was the elevator going up and then it stopped, or was it going down and then it stopped?
When it opens and stops.
Okay, well, you guys tell me, how do you feel when the elevator's going up and then it stops? Do you feel heavier or lighter? Lighter. Okay, that's fine. But so tell me, during what part of your trip do you actually feel heavier? What's that?
You're gonna go down.
Okay, when it's going down, wait, when you want to start going down? Okay, when you stop on the way down, okay, beautiful, that's correct. But are you feeling heavier for the entire trip or only at the end? Yeah, only at the end. So DeAndre says, hey, if I'm going down and I come to a stop, I'm going to feel heavier. What's the other circumstance where you would feel heavier in an elevator besides going down and coming to a stop?
Starting to go up.
Go ahead.
Go
Cool.
up at the start.
Yeah, when you go up at the start. But I want you to see that you're not feeling heavier the whole trip. You're only feeling heavier at the beginning. Because what's happening to you at the beginning of the trip when you're going upward? Yeah, you're accelerating. It has to exert a force up on you, correct? Well, that gets us to the topic of apparent weight. And the first definition of apparent weight is just how much you feel that you weigh. That's good enough. Apparent weight. How much you feel you weigh. You feel heavier at the beginning of a trip upward. You feel lighter at the end of a trip upward. You feel heavier at the end of a trip downward, and you feel lighter at the beginning of a trip downward, right? It's just how you feel. And this is all, this class, we're all about feelings, right? I always protect your feelings and make sure that no microaggressions. No trigger warnings. Or should we do trigger? Well, enough of that. But you know what? As much as I value feelings, we can't just depend on feelings. We need some way to quantify this feeling of being heavier or lighter. I want to quantify it. I want to assign numbers to it. So here's what I'm going to do. Here's my elevator. Here's me. And I'm going to put myself on top of a bathroom scale. So is that okay? I'm now standing on a bathroom scale, the type of scale that tells you how much you weigh. Alrighty. Let's say this elevator is accelerating upward, okay? The force that's accelerating the elevator upward is the cable, right? The cable's attached to the elevator, and the cable pulls on the elevator, and the elevator goes up. It accelerates upward. But the cable's not attached to me. Tell me, what force is making me accelerate upward? Good, the floor, except I'm not even in contact with the floor. What am I in contact with? The scale. So do you guys agree that it is the scale that's accelerating me upward, right? If I'm standing on a scale and I'm accelerating the upward, the only thing that's making me accelerate upward is the force that the scale is exerting up on me. And whatever force the scale exerts up on me, what force am I exerting down on the scale? Like if the scale was exerting 200 pounds up on me, how much force would I be exerting down on the scale? 200, right? Newton's third law. Whatever force the scale exerts on me, I got to exert back. Which means I can actually read the scale and determine how much force the scale is exerting on me. Well, what do we call that force that the scale is exerting on me? Yeah, normal force. The scale is exerting a normal force on me. And yet the reading of the scale is going to tell me how much I feel that I weigh. And so that gets me to the next thing, apparent weight. It is the normal force acting on you. That's your apparent weight. The scale reading, which is the normal force acting on you. Your apparent weight, the normal force acting on you. That's what your apparent weight is, the normal force. Yes?
Is normal force the same thing as support force?
Yes.
Okay.
Did you have college prep physics last year? Then yeah, what they called support force, we call normal force. It's just, I don't want to call it support force because that kind of implies that it's always acting upward, supporting you. But in this class, normal force is going to be in all directions, in any, whatever direction I happen to choose, you know? But yep, it's the same thing. So the first thing I want to say, yes?
I checked the loss of problem.
What does this bag consist of?
It's that has like my girdle and then the shirt I wear underneath my pads. And it's just
Okay.
other stuff.
Okay. Wow. So it's in a red Adewanda looking bag sort of thing?
Red like an Adidas bag. It's like a drawstring.
Wow. I don't remember seeing it. Has anyone seen an Adidas drawstring bag? Maybe someone played a trick on you and hid it? Yeah, I don't remember seeing it like after class, but I'm not sure. I'm so sorry. What a huge
So it's
hassle.
suspended in the air, but it holds your weight.
Check my
Decent football, not wrestling.
Same thing.
And you sure you brought it to school?
I mean, they're all stupid tall white guys running at each other and knocking each other down.
And you have some friends you sit
That's
next to.
great,
Could
Lynn.
one of them
That's
have grabbed
great.
it for you?
I mean, they let half the before I did.
Okay.
I'd hem them up. Well, where's my bag?
All right, well, Caleb, I don't know, man. You're welcome. Good luck. What a bummer. Wow, what a bummer. Although maybe it's God telling him to stop playing football. Yes, sure. I don't know, have you read, I mean, just, there's this, another kid died playing football. We've got a kid in like South Carolina or something, died. So there's been 2 deaths now. The season's like 2 weeks old, 2 deaths. Football, rah-rah. Okay, so
There's a lot of physics in NASA.
So I just want to tell you
This is where there's a lot
the
of football.
apparent weight, whenever a problem in the textbook or a problem on the AP exam asks you for your apparent weight, they're always asking for your normal force, because that's always going to be what the scale reads. Alrighty? So let me give you a problem pertaining to normal force. Just one second, the interruption made me lose my train of thought. Yeah, okay, so here's what happens. Here's a next example, okay? A 750 Newton dude standing on a scale jumps up. The maximum reading of the scale is 850 newtons. Find his acceleration. Now, are you guys okay with this idea that if I'm standing on a scale, it normally reads my weight, but if I jump off the scale's going to read more than my weight? You guys okay with that? How many people here have cats or dogs? Okay, has anyone had the experience of a cat or a dog is on top of you and then they jump off of you?
Yes.
And how does it feel? Yes, exactly. I go, yeah. Especially if they're like right on my diaphragm, and then they go, and the little kitty goes jump, and then it's like, ugh. So you know it exerts more force than little kitty's true weight. Okay, please do this problem now. Give me a free body diagram. Sum of the forces equals ma. Good luck. I'll even get you started on the free body diagram. Here it comes.
Thanks.
Okay, great. Good luck. Big fat dog. Okay, I see that your microscopic free body diagram. Can you see the numbers? No, the scale is giving up 850. The weight of the Earth's gravity is 750. Are you guys okay? Make sure if the scale reads 850, that means the scale is exerting a force up of 850. And so because it's exerting a force up of 850 on you, you're going to exert a force of 850 back on it, and that's why it reads 850. But the scale is exerting a force up on you of 850. Earth's gravity is exerting a force down on you of 750. So make sure you got just two forces, 750 and 850. It's like if people do the free body diagram correctly, they'll probably get the rest of it correct. Yeah, there's only two forces actually. The 850 that the scale exerts up on you, and the 750 that the Earth exerts down on you. That's it, just two forces. Ooh, one. Yeah, good. Now do some of the forces equals ma. Oh, you did it already. Oh, cool. Then on the left side of the equation, you should have 850 minus 750. And on the right side, you should have 750 divided by 9.8 times 8. Yes, good for you. Yeah, everything you're doing is correct. Good job. Yay. Oh, we're so smart at this part. That's 850 up. Yeah, 850 up, 750 down.
Oh, the
And then do some of the forces equals ma. Yeah, perfect. It's all good. Oh, good job. Yay.
So if I was to define this positive, that would be plus the
No, the 9.8 is never negative. When you're converting weight to mass, you never do negative for the 9.8.
Oh, okay.
It's just 9.8 divided by whatever. I don't want to.